Now, with that, it sounds like Kepler came across this really easily. Like all he did was take the data and draw in, and he went, boom, ellipses. But the reality is, the first time he tried to fit ellipses to the data points, it didn't work. At least it didn't seem to work. And so he tried for 6 months to get other shapes to fit the data points, and then he finally wadded everything up and threw it in the trash and started over. And he tried ellipses again, and they actually worked. And one of the problems is these are a lot of numbers, and these are a lot of very difficult calculations. He didn't have all the calculational tools that we have today. He had to do everything by hand. And if you look at his notebooks, you see that they were kind of a mess. And so it took him a good 6 months to come up with just his first law, which means that if you're struggling with some of the mathematics here, it's okay. The best mathematician in the world messed up his math. All right, so once he had the shapes of the orbits down, then it was a matter of trying to figure out other behaviors. Were there other things that the planets were doing that he could explain? And one of the first things that he noticed was that when he looked especially at a planet like Mercury, that it got a little closer to the sun and a little bit farther away from the sun, and as it did that motion, a little closer and a little farther away, it also changed its speed. So here's the planet Mercury in its orbit. Now the planet Mercury has a pretty large eccentricity of 0.2, and so you can definitely tell that the sun is not sitting in the middle. And there are points when Mercury is far away from the sun and close to the sun, and if you watch this orbit long enough, you might be able to persuade yourself that Mercury is changing its speed. Now without the aid of calculating anything, you're not really going to get that. But if you can get a hypothetical planet with a really, really eccentric orbit, you can start to see the difference. As it gets closer to the sun, it really seems to whip around, and as it gets farther away from the sun, it slows down. And that is the essence of Kepler's second law. What Kepler's second law does is it relates the speed of the planet and its position in the orbit. And the official textbook definition is that the radius vector connecting the planet to the sun sweeps out equal areas in equal times. Now, that's kind of hard to describe, so what we'll do is show you in this simulation. So here again we have the hypothetical extremely eccentric orbit for a planet. And as you start the animation, you see that it definitely gets faster when it gets closer to the sun. Now, what it means for the radius vector to sweep out equal areas in equal times, you just imagine that you have a line drawn between the planet and the sun, and just see how big of a pie slice it sweeps out in a certain amount of time. So you could start this and you see a sweep. Now this is a long, skinny, sort of triangular shape, and this arc length here is pretty small. And the planet covers this arc length in a particular amount of time. Now if you look at this radius vector when it's closer to the sun, well, it's a shorter radius vector, but you're still getting the same area for the two sweeps, which means that when this planet is close to the sun, it is going through a much longer arc length, which means it's going faster. So to recap a little bit, Kepler's first law told us about the shapes of the orbits, that those were ellipses with the sun at one focus point. Kepler's second law told you how a particular planet would move during the course of its orbit, slower when it's farther away from the sun, faster when it's closer. Now Kepler's third law, which took him about 10 years to figure out, related planets to each other. And what he found, which is not terribly surprising, is that the innermost planet Mercury gets around the sun much faster than the planet Jupiter, for instance. But it's not just a one-to-one relationship. What he found out was that the orbital period of each planet squared divided by the cube of the semi-major axis always gave you the same constant. Now, on this simulator, it shows p squared equals a cubed, but that's not strictly speaking entirely true. What is true is that the orbital period squared divided by the semi-major axis cubed always gives you the same number. And when you graph that, you find that the planets Mercury, Venus, Earth, Mars, and Jupiter fall on this not exactly straight line, but not really exaggerated curve. So you've been through Kepler's laws now, and you know how things move in their orbits around the sun. Now remember, Kepler doesn't understand why these things are orbiting the way they do. He just knows they are orbiting this way. He had no idea of the fundamental things that were involved in causing these motions. But if you skip ahead about 70 years, you come to Isaac Newton. Now Isaac Newton, as legend has it, was sitting in his orchard one day and he sees an apple fall. But that's not actually the end of the proper legend. The proper legend goes he sees an apple fall at the same time that he sees the moon in the sky. And he thinks, what is it that is causing this apple to fall, but not causing the moon to fall? What's happening that's different? Why is the moon not falling to Earth? But then as he considers it a little bit more, he realizes, but the moon isn't going in a straight line at a constant speed, so there has to be some kind of force involved. Now, if you look at the orbit of the moon around Earth, or you look at the orbits of the planets around the sun, it probably looks somewhat familiar. It looks like circular motion, and you've already dealt with the centripetal accelerations that are involved in that and how you come up with them. And so that's exactly what Newton did. He went back to the drawing board and he started to consider what the numbers were that were involved in having the moon go around Earth and having an apple fall to the ground. And as it turned out, he did find that they were tied to the same thing.